Okay, so welcome to the second. I can't believe we have a databases track at Lambda Jam. I never thought that that was going to be a thing, but welcome to the second talk in the databases track, and I'm looking forward to the third one. So I claim that functional programmers spend too little time thinking about how we interact with databases. When we do think about them at all, it's often in terms of, like we just heard, so how can I write a type-safe ORM so that I don't have to deal with SQL, and I can just think in terms of my favorite functional programming language, which can be great, and it can be useful, but it's not the same question as, what is the most effective way for me to deal with the data that lives in this data store? Because I claim that the answer to that question is sometimes, well, have you tried SQL? I think it's too easy for us to treat the data store as, ew, how icky and mutable. And so our focus goes straight to, how do I get the data out of there as quickly as possible so that I can handle it in the application layer in my nice pure functional programming language of choice? I'd like to put those other languages aside for a moment and think about the tool that's already built into the data store itself. Think about SQL. And I should say, by the way, I do absolutely agree with Dave from the previous talk that there are many, many ways in which SQL is horrible. I'm not here to tell you that it is the perfect functional programming language, but it's there. Unless you're using tutorial D or something, we're using it anyway. And I think it's worth diving further into because sometimes wrapping a black box around something that you don't, just because you don't like it, just creates complexity. So, some expectations management right at the start. I said I'm not going to be talking about how can we create some type-safe ORMs or anything like that. I don't want people waiting for a big reveal that's not coming, right? The FP that we're going to cover in this talk is basic, it's uncontroversial, and look, SQL doesn't have higher order functions. There is a limit to how fancy we can get. We're not up the top here with the functors and the monads. We're down at the level of sort of, yeah, let's make the most of what we've got, right? But the interesting part of this talk, I hope, and what I hope you will take away from it, is that we can apply at least some of our basic FP techniques in a context, and in particular in a language, where we might not normally think to do that. While we're on the subject of expectations management, by the way, at the end of this talk, it's going to feel like I've hardly shown you any code you couldn't have figured out how to write yourself. And probably, oh yeah, if I'd thought about it for a little bit, I would have thought of all of this myself. I hope you'll forgive me for that and bear with me through the talk anyway. What I really want to achieve today is to shift your perspective subtly more than to teach you new things. So I want you to see data transformations that we do in SQL as fundamentally the same sort of stuff as data transformations that we do in other app layer languages. It's just done on a different computer. So fundamentally, I want you to think of SQL as a programming language. Sometimes a shit one, but a programming language, and sometimes it's worth using. So my aim over the next 20-25 minutes is to show you how some of the basic FP techniques that we all know and love can be used effectively in SQL. And when I say that we're going to be using FP techniques in SQL, I mean we're writing some SQL functions, and a lot of you are probably going to look at me and say, but Sam, that sounds like a pretty pointless talk because I don't really write any SQL functions. I don't write stored procedures. So I really need to start, I suppose, by convincing you that actually maybe you should do at least some more work in the database itself. Then I convince you that then I can try to convince you that while you're there, you should be doing it functionally. Hopefully that'll be the easy bit. There's an elephant on this slide, by the way, just to be upfront about it. When I say SQL here, I don't think I'm going to be showing you much that can't be done in just about any database. I use Postgres, you should too. Your mileage may vary if you're using other implementations. I think most applications these days take the approach that the database is for storage only. It's disks, it's not compute. When you want to do something with the data that lives in the database, first thing you do is get that data out of there into a nice safe zone of your functional programming language. I think that's kind of weird because a lot of very smart people and much, much better programmers than I will ever be have put a lot of very productive effort into building for us these specialized tools for data munging. And what we do with them is we say, I'm going to put my data in there, fine, but I'm going to treat it as though it's some simpleton manager of flat files whose job is to take care of those nice ACID principles, but that's all. I'm not going to do any data munging there. I'm going to pull it out into a higher level application language and I'm going to do all of my data munging there. And honestly, the closest we really come to bridging this gap of our general purpose programming environment and specialized tool for data munging is, oh yeah, we should probably avoid doing n+1 selects. That'd be a bad idea. I think we can do better than that. I think the reason that we've ended up in this position is partly as a sort of a hangover from the enterprise Java days. I think 10 or 20 years ago, the architects on high were all telling us how absolutely critical it was that you do none, I repeat, none of your work in the database, and instead you do it all in the web tier and the app tier because that's where the magic of horizontal scaling can happen. And I think there's a couple of problems with that. I think even if it was ever true, it's maybe not true today. One of the problems is, I think actually databases scale pretty well for most applications. If you're not dealing with terabytes of data, and if you are, then maybe you're looking at doing different architectures entirely anyway. But often, actually, vertically scaling on a modern cloud provider, vertically scaling a database is a pretty feasible thing to do. It's not hard, it's not expensive, it's not likely to fail. And to be honest, horizontally scaling the database by chucking some read replicas behind it is actually also pretty straightforward these days. And so I think a lot of the reason for, no, you must do all the scaling in the web and the app tiers falls away. But I think there's also another problem, which is even if your nice theory is that you're going to do all of your scaling in the web tier and the app tier, all you're actually doing is, okay, let's get the data off to a different machine and I can horizontally scale that machine, and there, I have no scaling problems. But actually, the bottleneck wasn't necessarily the thing that you've now scaled out. The bottleneck is often, I need to read this stuff from a disk. The bottleneck is often I/O. And in fact, if you're pulling all of this data off of your database into your application layer, sending everything across the wire before you do any processing, actually, you've often made your process worse because you've told your database, no, you have to go read all the data. I'm going to do a lot of my filtering over here. And not only do you have to read it all, you have to serialize it all over the wire. So I think there's a couple of reasons why we just shouldn't follow this enterprise Java rubbish anymore. So at this point, I'm going to decide just on your behalf that you're all convinced that there's no architectural or performance reason that everything needs to be pulled into the app layer before we do anything interesting with it. I realize that's sort of the whirlwind overview and that many people will want to argue that point, and I would love to argue that point with you later out in the hallway track. But for now, I'm going to assume that we're up for writing more of our logic in SQL. So long as I can convince you that it's possible to do that in a way that is not fundamentally terrible and make you going to cry. So it's probably helpful at this point to give you a few really, really basic examples of what putting more of that work into the database might look like. And I mean really basic. Don't expect to be wowed by the amazing power of the code in the next couple of slides. One of the things you might want to do, for example, if you're putting a little bit more of the logic that is currently in your app layer, shifting that across down into the database, is a JSON transformation. A lot of the time, I see a lot of code bases with app layers, which are basically run some queries to get some stuff out of the database. Your app layer, all this marvelous transformation that you're doing purely and functionally, is mostly just, I ran a couple of queries and I turned them into JSON. You can do that in the database, save yourself the work in the app layer, and it's actually not even particularly complex to do, and it doesn't muddy your SQL and make it look too horrible. It's especially useful, by the way, if you have one-to-many relationships. So I haven't shown an example with a one-to-many relationship in here, but if you had a field which was comments or badges, so that we're dealing with a Stack Overflow data set or something, then you can do that aggregation here in the database side, where if you're doing it all in the app layer, you're going to be running at least 2 and probably 3 queries. Some of you are going to hate this example, I suspect, because it just looks icky and wrong because you're combining multiple things into one select statement that are actually completely unrelated. I'm going to claim that you should think about doing this anyway, at least on some occasions, because really, where you have a piece of code that in the API wants to go and get 3 bits of information and you're executing 3 SQL queries and then doing something with the results, doing that on the other side of the network cable in the database is actually fundamentally no worse than doing it on the application side of that network cable. I suspect some of you will never agree with me on that, and so I'm just going to move on though. Even if that one wasn't to your taste, this one should be a bit more within your comfort zone. What we're doing here is using a function for one of the many things that functions are good for. So on the left-hand side, we have a query that is doing a left join. I'll tell you about lateral in a moment. That is doing a left join to something that is being pulled from a function. So we have extracted some logic that we could have just written inline in the query there, but we've decided that maybe this is reusable, maybe this is something that deserves a name, maybe this is something that needs a unit test, whatever. We've extracted a function, made it a named thing. And so that should all be pretty familiar. And I think that's something we don't think about doing in databases very often, and that can be quite useful. So we're now a bit more than 10 minutes in, and what have I actually shown you about doing FP in SQL? Bugger all, that's what. So let's take a step back a moment, talk through what approaching SQL functionally actually looks like at a high level. And this is kind of the core groundwork that I want to lay for the rest of the slides here this morning. I think I imagine you have probably heard of the notion of writing functional or FP software with a functional core and an imperative shell. So that's a principle described by Gary Bernhardt in his Destroy All Software series, and I think it's a really good FP principle. And I think it applies reasonably well to SQL, if you sort of squint a little bit. I think when we're approaching writing SQL and we want to try to do things functionally, we can think of the imperative shell part of the SQL that we're building up being the bits that are specifying the tables that we're reading from, the global mutable state that we need to be able to pull in, gathering all that data together in the from clause. That's all the imperative shell bit. You're reading global mutable state, it kind of has to be. And then after that, you're doing data transformations, you're doing filtering, and all of those are things that can be done functionally. And we don't tend to think separately about those in database terms, and I think we should. The stuff that needs that global mutable state and the stuff that can be pure functions. So in addition to doing that sort of heavy lifting at the outermost level on referentially transparent functions inside, the one big thing that I am going to press in this talk is that we're going to need to write everything so that it ends up being one SQL statement. That might sound slightly ridiculous, but it sounds slightly ridiculous in a SQL context because we're used to seeing stored procedures that have sort of step 1, step 2, whatever. But if you think about this in a Lisp context or a Lambda calculus, it's actually quite common to say, I'm going to insist on everything being just one expression. There might be arbitrary nesting, use subselects, whatever, but everything has to be one expression. Without really explaining it too much, I'm going to insist also that we're using language SQL in Postgres. This is telling the database. This is actually just one SQL statement rather than PL/PG/SQL, which is the procedural language within Postgres. So, functional programming, how are we going to do that? Functional programming is all about MapReduce, right? So this is the context that I want to put in your brains. When we introduce functional programming to people who maybe don't know very much about it yet, we talk about often how powerfully general the MapReduce paradigm is, because FP is really good at simple individual data transformations composed together through generic collection operations. Obviously, MapReduce and associated functions operate on lists. I'm not going to jump into how foldables might exist in the database or whatever. I'm going to hand wave across whether we're talking about relations as sets or lists or whatever collections. I'm going to talk about them as things that we can map and reduce over. And so I want to walk through quickly the sorts of operations that make FP, list or set processing so powerful, and I want to show you the direct correspondence in SQL. So, map, I'm going to use some Haskell type signatures up the front just because it is LambdaJam and that's kind of obligatory. But I'm going to walk you through some of these functions. So map has a fairly simple function signature here, taking a function of A to B. We've got a list of A's. We're going to give you a list of B's. I don't think anyone would be surprised by the explanation that this is how you do that in SQL. I do suspect that probably when you look at this SQL, you're not so much thinking in terms of a map function, but I think you should. I imagine that no one's going to be particularly surprised that filter has a pretty good operation in the has pretty good database support, because we're obviously doing a lot of filtering, constructing a lot of predicates in our where clauses in the database. So I don't think there's anything that's a surprise here. Reduce is one that maybe you don't think about so much as turning up frequently in a database context. Aggregate functions, though, are in fact reduction operations. The type signature here is not one that you would find on an actual Haskell fold R or fold L, just because I've tried to be faithful to the way that Postgres actually represents an accumulation function, an aggregation function, but you can define reduce functions. This is the type signature that they would have if we were in a language like Haskell. Concat, probably not particularly surprising that you can concatenate two relations together in a database. One that maybe is a little bit more surprising is concat map. I promised earlier on that I was going to explain lateral joins. I suspect this is probably the only bit of SQL syntax that wouldn't be familiar to most people in this room. Maybe some of you have seen lateral joins before, maybe you haven't. The idea of a lateral join is that it allows you to define the right-hand side of the join, the relation on the right-hand side, as one which, for each row that appears in the relation on the left-hand side, does something and returns a result set. So it allows you to, and I'm going to jump to an example, it allows you basically to say, for each thing on the left, maybe I want 0, 1, or many things in the relation on the right. So my stupidly contrived example here is maybe we've got up the top here, we've got a table of competition entrants, and we've got their names, and we've got how many times they've been entered into the competition, and we want to get a result set which is, okay, well, John's entered 3 times, so I want him there 3 times. Alice has entered once, Bob hasn't entered at all. Lateral join is how you would do that, and in Haskell, that would be a concat map. So that's great. We've seen how there are sort of SQL, I suppose, correspondences to some core higher order functions that we have in functional programming languages. Now what? How do we go forth and use that information to write functional SQL? And this is the bit where I stand up here and feel really stupid, because the way to write FP in SQL is the same way as you write FP in any language, which is that you write pure functions and you compose them. So let me show you what that means, but before I do, let me just emphasize that when I say pure functions, I mean it. So certainly we're going to want to avoid mutating or otherwise side-affecting functions, but a lot of the time we're also going to want to write fully referentially transparent functions. So functions which depend only on their actual arguments and don't, in database terms, that means that they don't reach out and read from arbitrary tables in the database. And the reason for that is reading arbitrary tables in the database is basically accessing global mutable state. I do have a caveat here. I say write mostly pure functions. I'm saying that because you will want to write some functions which go out and read from arbitrary tables. Those are going in the imperative shell bits. So when we're writing the sort of functional core parts, when we're writing the map and the filter type functions, rather than stuff that we might put in the from clause, then those are the ones we want to be referentially transparent, please. So trivial example, okay, what's a pure referentially transparent function? You want to write the thing on the left rather than writing the thing on the right, okay? You want to just take in the arguments that you need in order to be able to construct the result without having to read from anything, rather than saying, okay, well, I'm going to take basically a pointer and I'm going to dereference it to go and get the things that I then need to concatenate together. It's this level of simple that is the sort of FP that I'm encouraging you to write. So on the left, good, on the right, bad. Worth noting, by the way, that Postgres does actually have a specifically built-in concept of whether a function is referentially transparent or not. You actually, if you tell Postgres that this function is immutable, then you're telling it this is referentially transparent, and you can do query planner optimizations safe in that knowledge. If you say it's stable, you're saying I'm doing a data lookup somewhere in this function, and that might affect the way that the query optimizations that you can perform. This is very similar to the previous slide, but I just wanted to chuck it in here to demonstrate that, in fact, you don't just have to have functions which take only scalar values. You can actually have composite types in the database. I'm not going to go into any sort of type theory in the database context, although that's kind of interesting too. But you can construct, you can pass in whole rows of things, or you don't just have to be stuck with first name, given name. Sorry, given name, family name. I said that one reason that we want referentially transparent functions is that that's just because what good FP programmers do, and we want to be good FP programmers. The other reason that you really want to do that is to support inlining. So if I don't have this slide, someone is going to ask a question as soon as I finish talking and say, well, but how about performance? Isn't going to be terrible. One of the things, if you do restrict yourselves to just doing FP style SQL, one of the things that you can get is the sort of optimizations from a SQL query planner that you might otherwise get from an FP compiler. You're not going to get as sophisticated as, say, GHC, but you can. These two queries on the right, where basically this function is being, I've manually inlined it in there, these have exactly the same query planner. Sorry, these have exactly the same query plan. The optimizer is smart enough to, it's smart enough to do things that are bigger than fits on this slide as well, but this is the example that fits on this slide. So we wrote some pure functions. That wasn't too hard. We now have some reusable pieces that we can pick and choose from when we want to build up the full functionality we're trying to implement. How do we put them together? And this is where I am going to take a little bit of issue with something that Dave said, which is you can't compose SQL. In fact, you can. It's not especially pretty, and it's pretty basic, but you can actually take one SQL operation and sort of pipe that in to a second SQL operation. So you can, if you want to map twice over something, you can do an outer select from an inner select, and in fact the query planner knows that it can collapse these together much the same way as we know in Haskell that this equivalence holds. You can combine filters as well, so again you can compose two filter operations together, and in fact that's equivalent to applying both of those predicates at the same time. So again we've got basically some FP. FP is giving us sort of insights that we can get these sorts of combinations for free. This is a slightly more complex example just because mapping of maps and filtering of filters seems a little bit overly contrived, even though that's honestly mostly what you're doing. You can also combine a concat map and a map to get a concat map. And yep, this is not the prettiest, certainly the one on the left, not the prettiest query in the world, but actually these are relatively straightforward, reusable chunks for us to reason about. And again, this is with our friend the lateral join. So we've written some pure functions, we've composed them. What else do we need to do? Again, I'm kind of almost embarrassed to say it because it feels like I haven't shown you anything particularly complex or fascinating, but the answer is, to be honest, we actually don't need to do much. If we are going to write SQL slightly more functionally, I think the other thing that we typically do is, in existing SQL code bases that don't take this approach, is we don't treat it like real code. So my answer to what else do we need to do to get good FP SQL is you need to treat it like real code. It's not just the ugly bit on the edge, which is how you get something off the disk. It is an actual piece of code, it needs tests, it needs some sort of an API, whether that's functions or whether that's views or whether that's whatever. It needs thought. And you need to think about reuse, separation of concerns, abstraction, etc. I think once you've got the understanding of, hey, we can treat SQL as a language where it's possible to do functional style programming, then it becomes a lot more natural to take these additional steps of, okay, and I'm going to treat that SQL like real code. Beyond this, there are other inspirations that we can take from the functional programming world when we're looking at SQL and databases. It doesn't necessarily stop here just because sort of that's all of the amount that I can present to you in one talk. I do want to at least give a pointer to to future possibility of bringing more FP principles in. There are some great FP principles. One of the things that functional programming languages, I think, typically do extremely well is they're very good at modeling time explicitly. Thanks. And I think if you move that into the database, I think we're getting much better these days at thinking about how we might treat our database as sort of either an event streaming, a record of an event streaming system, or in any case, something which models facts which arrive and potentially change over time. One of the other principles that functional programming is really big on is immutability. I think what you want to do is you want to model irrefutable facts in your database so that you don't have to go and change them. You want to come up with a model where you can say, it will never change that this particular fact was true between these timestamps, for example. So I think there are other ways that we can look at taking FP principles and applying them to the SQL that we write once we've gone beyond this very basic, hey, this is how I do maps, filters, concat maps, whatever else. I do want to show you one additional thing that I suspect many of you, even after all of this, will find a bit icky. One of the questions that led me down this path was, I've got a CRUD app in a side project where really I felt like the app layer wasn't carrying its weight. Because actually all I was doing was data transformation, and if that's just turning stuff into JSON after doing some data-munging, well, the database can do that. Actually, all I need is the HTTP server. And so to point you in one of the directions I've taken this is the sort of request that my app layer now receives as an HTTP request. This is the front end saying, I want you to call the get schools stored proc in the database, and I want you to call get classes, and I want to call you to call get statistics with this start date and this end date, and I want you to give me back the result. And so that just gets transformed into this, and all of this code lives in the database, and all that sits in front of it is an HTTP server that just calls a function with literally a JSON payload that it got off the wire. I'm not necessarily suggesting that all of you should go away and implement apps which take it to this extreme, but I think it's quite interesting that this is possible. One of the things that I find with an app that looks like this is debugging it is actually really easy, and testing it is really easy because there's only one place that I have to go. I go look in the database, the data is there, the code is there, I don't have to combine these two things. Like I say, I doubt you all want to go that far, but I hope you will at least come a little further than where you are right now. Thank you very much.